Hi. So in this example, we're going to explore different fracture types and different ways to think about fracturing, as opposed to our previous sessions where we did a generative approach, meaning start from nothing and generate what's happening. This would be more of a subtractive approach. So we'd probably take an existing piece of geometry and figure out what to do with it, parse it, and get it ready for destruction. So there's been really great artist-driven innovations into rigid body dynamics, particularly in Houdini 18. But it's important to understand where all these innovations come from and what all these innovations are based on. And so we're going to take a very fundamental look, even though we'll be using the latest bullet simulation technology. Okay, so the first example is we're just going to drop a bunch of boxes, and these would be mimicking bricks. Now, the huge thing about dynamics that will not change is everything is relative to scale. So I highly recommend making a box or something in your scene that resembles the size of a human. And then we know everything else is based on that, because there's no way to get a simulation to behave better after the fact, after all the hard work is done. So definitely take time into making your simulation play at the right scale. Okay, so starting with a brick, we'll just make a few copies of this. So we can use the copy and transform. And maybe we just want to make about 10 copies. And as we do that, we want to raise them up in the air and maybe rotate them a tiny bit just to give it some variation. Okay, so that hopefully will be a little bit interesting. All right, and let's just raise it up in the ground so it has a little bit of distance to fall from. Maybe tilt it a tiny bit too. Okay, so here's our starting point. Now, even though this is done under the hood, here I've just made a RBD bullet solver, which is actually a DOPS network under the hood with lots of presets. And we can make our own, of course. I highly recommend still doing that for advanced setups. So even though some of the stuff is done for us, for instance, we can just plug this straight in and hopefully we'll get some cool results. But it's important to understand how the computer actually sees this geometry data, because internal to here, what we have happening is we have a partitioning going on where each object that's separated by its faces and by its vertices is treated as a unique bullet object in the simulation. But that can be changed. So simply to mimic what this is already happening here, I'm going to drop down a very old and highly useful node, which is connectivity. And I'm going to go to primitives, primitive, and we'll call this brick. So here we have 0, 1, and you can see the number will change as we find a group of unconnected faces. And we can base our name off of this. So with an attribute create, I'm going to do name. Now we have a name attribute, primitive. Okay, it's a float, so I'll make that a string. And here, if we just did that, if we just called this brick, all of these different pieces of geometry have the same name. So the simulation thinks that this is actually the same object. It doesn't have to play by the rules of what we see as logical. But what's actually happening is we're probably partitioning based on this. So here I'll go brick underscore and backticks in reference to that integer attribute that we created with the connectivity. So we'll go add brick. And now we can see we've simply just copied over the attribute and our simulation will behave as we'd expect it to. This really highlights the point of what a fracture actually is. A fracture isn't something that the computer just automatically decides. A fracture is whatever we make of it. So anything that we give a unique attribute to, a unique name attribute, will be treated as a separate fractured piece of our simulation. So that brings us to our next example. And here, let's define our own fracture. There's lots of awesome fracturing tools in Houdini now. They're blazing fast, they have tons of power, but everything is based on this idea of what's connected to what has a different name attribute. So here, we've started with a flat object, which could give issues during the fracturing process, and gone ahead and made our own very custom fracture. Could mimic a glass or some other type of material that you think would be a flat fracture. And it still behaves as if we had used default fracturing tools. Okay, so let's set this up. And we have to use a little bit of knowledge of attributes along the way. Okay, so starting with our grid, let's just make a null. Actually, let's just copy the grid. Okay, and I'm just going to remesh this. So we want to add some resolution because a fracture can't really function without resolution. There we go. Okay, so now let's make the actual core of the fracture, which is going to be a proximity to something. So here I'm just going to scatter some points on this. So that's going to be way too many fractures. Each point would represent a fracture. So let's turn this off, and I'm going to go by density. And actually that looks pretty good for now. All right. So in a VOP, we want to separate our polygons by what's closest to this point or that point. So diving in, I'm going to use the near point from the second input, meaning the scattered points, based on the current position. And now here, we could generate a random color. And this will start to look like a fracture. Okay, because it's really just getting the nearest point and forming a boundary of all the same value. Now, these are still connected surface, so we're going to have to treat that still, but this is the basis of the fracture. So I want to export this as an attribute. So I'm going to use a parameter. Let's call this fract ID, integer, invisible, export. Okay. So now our polygons have a unique fract ID. Okay. Now, this is looking really uniform. I don't know many things that would actually fracture like this. So how can we add some variation to that? So if we can't really distort our inputs, meaning that we can do different seeds all day long, it's still going to create very flat fractures. And we can change our grid geometry, but it's still going to create flat fracture lines. For instance, putting a noise on the positions. Just using an anti-alias flow noise here. You see, it's no matter what we do to it, it's still going to create very fractured lines. Let's adjust our noise a little bit though before we move on. Yeah, so no matter what we do, we can't get away from these lines. All right, so instead of changing the result of our operation, we'll change the input like this, and then we'll go back to the input state when we're done. So for that, I'm going to use a rest position. So the rest is really just copying the position from here to here, from here to here. It's just a set of attributes. Okay. And we can deform it. We can stretch it. Maybe we want to make that a little longer or shorter. Okay. And we can even scatter on it. And we've still got flat fractures. But here's the thing, is that now we can set this back. So we can use a point wrangle or a VOP, up to you. And I'm going to set the position back to before it was distorted, up to the rest here. So vector at capital P for position equals, and we're going to set this based on another attribute. So I'll go set, let's see, vector at rest.x, vector at rest.y, vector at rest.z, and then close. So now we've got some distortion because we've distorted our input, and now we can see that as we move along our noise pattern, we're getting different qualities of our fracture. Okay, so let's add a touch of roughness here. And it really depends on, we can get different results from changing the input of our scatter. But yeah, now you can see that we're distorting the position, and so the near point is getting different distorted positions based on that. Okay, so now how do we separate out these things in a seamless way? Well, we can base that off of our fracturing ID. So our fracturing ID right now, fract ID, is going to be different every time it found a different closest point. So we need to get that onto the primitive so that we can separate out the faces. So I'm going to do an attribute promote, and we'll promote the color while we're at it as well. So I'm going to go promote CD as well as fract ID from point to primitive. Okay, now the problem with average is we're going to get a lot of values that we never actually had before here. So I'm going to choose mode. And what that means is it's going to pick the most common occurrence. It's only going to pick this one or this one. And if the polygon shares this of its points, it's going to go with the one that has the most of that. And that's going to get us a really clean fracture here. And now let's break it apart. So we can use a for each for that. For each primitive. Now be careful of for eaches because they're generally really useful, but watch out because they can change topology. And it's actually, this function's like a delete node. So if we delete something in more than one place, we're actually copying the points. So here, I'm just gonna say fracture by piece attribute fract ID. And now we should be separating out individual pieces, as we can see here. And we've actually changed the point count in doing that. Our points used to be 4801, and now they are 5371 because we've doubled the points on all the edges here. Okay. So what do we do next? Well, now I want to smooth this out because this isn't looking too great, all these jagged edges. So we could do a smooth. And let's turn off the group boundary. And let's turn up the strength a little bit. Okay. Make that nice and smooth. All right, so we're getting some smooth edges here. Looks fine. So, but now we've got these gaping holes. So how do we get rid of that? Well, once again, we can use low-level attributes pretty efficiently. So remember that this point and this point are the same point. They are just got copied. So if we tag that with an ID ahead of time, then we can draw a similarity downstream. So I'm going to do an attribute create here. Let's call this point ID, point integer at point number. So here we're just copying over the point number to the ID, and let's just add 1 just so we avoid 0 values. Okay, but yeah, and now in certain occurrences we should see a duplicate. For instance, there's 2 point ID 1s. That must have been where it's separated out. Okay, so now I'm just going to use one of the most tried and true nodes of Houdini, the add. And let's just delete all of the edges here. For that, we can use find the edges first. We can use a group. Let's see. So disable that. Edges, we'll call this open. And we're going to group by edges, unshared edges. Okay, so we found the open edges. Let's isolate those with a blast. Non-selected. And let's get rid of, in the add, let's get rid of all the geometry. Now we just have a collection of points. And then let's make new polygons out of those. Polygons by group, by attribute, and if they share a point ID, they'll make a polygon. There we go. And now let's scale that. Primitive. Do transformation. Let's scale that to nothing. And when it does that, it's going to scale about its centroid. Okay, now finally, once again, these still have a point ID. We can copy over the positions as long as the point ID is present in here. So copying all the positions doesn't work so well, but if we match by attribute point ID, now we've got an average by making our average positions with these polygons of our smooth geometry, and now we got a nice little smooth on these pieces. Okay, and they're separated out. So let's finish this off with a poly extrude. And let's do a output everything, and we're going to do a transform global, and let's just extrude out a little bit. On this axis. And now let's test this out. There we have it. So we don't actually need all of the more advanced fracturing tools. They're very useful for workflows, but there's always going to be a situation that arises that we need a bit more control. So keep your backbone of Houdini knowledge and SOPs handy, because you might always have to do something a little bit out of the box with that. So now let's explore three-dimensional fracturing a little bit. So starting with a tube, I've gone ahead and done more of the older method. It's not really used for anything that has to look good, but you could use it for more utilitarian tasks. So starting with a tube, I'm creating a volume with a VDB from polygons, scattering, and then have the Voronoi fracture. And that creates those straight cuts, just like we've already experienced. Okay, so let's bring our little tester up here. And let's drop this on the ground. Okay. Now there might be some uses for this, but overall, we're not going to get the look we're after because we've got these very hard edges that are present, and that doesn't resemble anything in nature that I can think of. So fracturing has really gone towards volumes, and even the upper level tools, they're still going to rely on volumes in their core. So let's make our own voluminous fracture using VDB technology. So let's start with our tube here. Like in the previous exercise, we need a collection of points to base our fractures off of. So scattering on the surface won't work because we need internal fractures. So we need to make a VDB from polygons. Okay. And let's turn this to a fog VDB, which has internal density. Make that a bit more accurate with the lower size. And here's our points. And now I'm just going to turn off these, and we can go and dial in a density that will stay consistent even if we change the size of our object. Okay, so here's a little scattering there. And now what I like to do is I like to base this fracture off of lines of motion, of stress. So for that, I like to use some boxes to cut apart the volume. All right, so I'm going to make a box. And this box is just going to be a little bit longer in the center axis, the z-axis, and a little bit shorter. And that might create a pretty nice appearance of a flowing fracture line. Okay, I'm just going to set the centers back to 0. Okay, so with a VOP, I'm going to give these things some random directions and random scales. We'll copy our box onto these points. So nothing happening too good right now. So here, I'm just going to generate a random vector. And let's fit that to the positive and negative axes. And go to the normal. Okay, so we got some random directions, and this in itself could make a pretty decent cut, but I want to vary the size of the cut lines as well. So for that, we can use the p-scale. So with another random, this time I'm just going to do one-dimensional output, and let's do a curve to remap the values, ramp parameter. Probably want smaller cuts more than bigger cuts. And then finally, we'd fit that to our desired range. So here's our desired output, minimum and maximum, and let's export that as a p-scale. Okay, so that's shrunk to nothing. So here we have a chance to remap the values. So maybe a focus on the smaller boxes here. And then I'm just going to make sure that we establish a decent minimum fracture size. So let's see, maybe when they're just overlapping here. And then the maximum fracture size, we'll just extend that boundary a little bit. Okay, so we've got a bunch of boxes. What are we going to do with those? Well, first, I want to give these guys some noise. All right, so we can't do that right now because they're just single faces. So we could apply a remesh. Oops. And let's make that a little higher res. There we go. And from here, we can apply a noise. Similar to how we applied a noise in our other example. Here's our noise. And this time we don't need a rest position because with a volume, we're going to be cutting directly and it can handle concavity. All right, so here, let's give this a little bit of care as to what we want our fracture to look like. So I'm gonna maybe up the frequency just a little bit. There we go, and impart some roughness. So that might look like a pretty good fracture. And now let's apply the VDB fracture. Okay, so the way this works is we're going to start with a VDB, a surface VDB. So as opposed to a fog volume, we want a distance VDB. And we're going to fracture this thing using this as a cutter object. So each one of these pieces is going to make a cut. Each one of these watertight pieces is going to make a cut. Now, a word of caution that VDB, having a lot of volumes in your view can overload your graphics card and cause crashes. So with one volume, this is probably going to be fine. This is actually just use one objects and then cut that out. We can see we've had some fractures here. But to use multiple objects, meaning separate cutters, I'm just going to view this downstream by a VDB convert. And we're going to view it only in the polygon form. Okay, so we're going to convert that to polygons, and I'm just going to bring up the parameters here, give it a save, and then separate cutters by connectivity. And that might take a little longer, but we've got some nice detailed fractures and allow cutter overlap. That's really going to take a lot of processing, but the result should be worth it. There we go. Now, if we wanted to get rid of these little indents here that could change the look of our object, the second input here is for a reference geometry. So we can use our original tube and it'll conform to the surface as best it can. And even though it might not be perfect, destruction isn't a perfect process, and when things are broken, they do look messy. Okay, so let's drop this in the ground and see what happens here. So as we can see here, something's a little off. Something's looking a little weird. And that's because the name attribute isn't really functioning properly. So this is an instance where we would have to have a knowledge of what's going on under the hood. I'm just going to copy our previous connectivity and name and reset the name attributes by connectivity. In this case, it was just creating a new name per cut, and with cut overlaps, that was presenting a problem. Okay, so now everything should be connected if it doesn't share faces. So after flip hooking that out, we can see that now we've got a fracture that's functioning properly, and we've got lots of size variation and an incredibly high quality fracture by following volume principles, and that gives us the concavity that makes it look good. From these examples, I hope we're able to take away how to bring geometry into simulations for the results you want. And that can be at a very low level, even though very high level tools and simulation paradigms exist. Thanks, and I hope you enjoyed the Houdini Fundamentals collection.